Meetings being recorded. Hold on. Okay, I think we're good. All right.
I think we should be good. I just started it.
Cool, cool. Thank you. All right, so that's what we're working on for today. So then tomorrow, what we're going to be concerned with is two things. So we're going to be thinking about families of line bundles. First of all, is this big enough? Do I need to make it bigger, smaller? What do people think? Is it good?
Looks good.
Okay, cool. So tomorrow we're going to be talking about families of line bundles on abelian varieties, and we'll be talking about dual abelian varieties, which aside from producing lots of examples of abelian varieties are also a useful structural tool. Then on Wednesday, we're going to talk about isogeny, which is the notion of equivalence for abelian varieties. So, whenever you study things, you have to know for yourself, what does it mean for two objects I'm studying to be the same? Torsion, which is about stuff that vanishes, and again, is an important structural tool. And then we will start proving, so I'll say start, the proof of weak Mordell-Weil. So I'll say weak, and then I'll just say MW for Mordell-Weil. But we probably won't finish it because there's a lot to say. So we'll finish it on that the next day, Thursday. This is the finish. Maybe I'll put a W here. And then we'll start something called height theory, which if you've never heard of heights, basically you should think of them as a way of measuring arithmetic complexity. And height theory is something that's been around for a long time. It has lots of generalizations, a lot of which I will not get into in this course. And then finally, on Friday, we'll finish height theory. There we go. We'll build our bilinear pairing. This, and then we will finish. So we'll prove Mordell-Weil itself. Okay. So that's not the right button. Hold on. There we go. I have to remember my shortcuts. All right, so what are we actually doing? So the first thing I want to do is get into Mordell-Weil. So maybe this will be our intro proper. So the classical Mordell-Weil is something that you're probably all familiar with, but I'll go ahead and remind you. So let's say we have E over Q, an elliptic curve. Elliptic curve. Then we're interested. Yeah, sorry, writing's a little slow with this thing. So we're interested in studying its Q rational points. So this is E of Q, and of course, there are multiple ways you can think about this thing, right? One way to think of it is it's maps from spec Q to E. Another thing is that if we think of E as being cut out by some equations, then this is saying, give me the points that have Q coordinates, or rational coordinates. So how can we study this thing? Well, one basic thing we might hope to say about it is it finitely generated, right? And the answer is yes. So theorem, and this I guess is classical Mordell-Weil. And that is that E of Q is finitely generated. And every time I write fingen, it'll be finitely generated. So what that means, sorry, pan down. then our Q rational points looks like any finitely generated abelian group. So it has a free part. That's not what I meant to write. Okay. It has a free part. So some number of copies of Z with a rank, and then a torsion part, which is often written with a subscript tors to indicate that it's torsion. So this is torsion. And of course, ever since this result came out, people have generalized it, and we'll prove a generalized version. And they've used it for a lot of different things, right? When you study elliptic curves, you can ask yourself, okay, what's the rank? What's the torsion part? What kind of groups can appear as the torsion? What does the rank look like in general? If I give you a generic elliptic curve, what's the rank? And there are lots of very famous conjectures and also theorems in number theory and in related areas that concern these kinds of things. So, we won't be getting into that, but know that this is the jumping off point for a lot of very important theory and a lot of really interesting stuff. So how do we actually get to the result that we want to prove? Well, the theorem that we're aiming to prove, which I'll just call general Mordell-Weil or just Mordell-Weil, is again a generalization. So let's see here. A be an abelian variety over a field K. And every time I write K, it will mean a field. So if I don't say it's a field. And I'll get into a second what abelian variety is. And K here is a global field. So again, I'll explain in a second what a global field is, but basically think of it as a generalization of Q. Then the set of K rational points, so again, the same sort of thing as we have there. Somebody have a question? Can somebody mute Leon, please? Okay, hold on, let me find my cursor. Where's it going off to? Ah, okay. That's so weird. All right, I'm going to move down just for that. Okay, cool. So, actually, as I said, there will be a few technical difficulties as we get used to this setup. So hopefully, let me move this. Okay, now hopefully we're good. Awesome. Switch back to pen. Cool. Okay, so the group of K-rational points of our abelian variety is finitely generated. So it's the same basic result, but again, the setting's a lot more general. So let's first understand what we're doing here. So I'll start with global field, right? So, in classical number theory, we often think about Q. And it turns out, especially in algebraic number theory, that if you're trying to study Q, it actually makes a lot of sense to study extensions of Q. So a number field, so I'll write it this way, is a finite extension of Q, by which I mean it is an extension of finite degree. And these things turn out to be useful. So which turns out to be useful in, let's say, algebraic number theory. Algebraic. Oh my, that's terrible. Yeah, sometimes it doesn't quite pick up my hand, but that's okay. algebraic, that's weird, number theory. Cool. Right, so you have the whole host of number fields, but then you also have a sort of flip side, right? So at the same time, we might want to study the following fields. So if I take finite fields, something of the form fq, where q is a prime power, and then I adjoin a formal indeterminate, this sort of thing is a field that appears a lot in practice. For example, we're looking at function fields of curves defined over finite fields. And, again, when you're studying these things, it makes sense to study their finite extensions. So I'll say that a global function field is a finite extension of this guy, right? So again, if you're getting a finite extension, then you could be extending from fq to say some fq to the n, and then you can't adjoin another indeterminate because that would give you an infinite degree extension. So you're going to be introducing some kind of polynomial relation on T. Okay. So one of the amazing things is that these two kinds of fields often end up having a lot of the same properties. You can prove things for one type of field and it transfers over to the other. And so, what we've decided to do over time is put all these fields in the same category. So a global field is either a number field or a global function field. Cool. So that's one thing down. What about abelian varieties, right? That should be A. Oh my goodness, that's terrible. What about abelian varieties? Right, so again, after I go through a bit on group schemes, I'll be able to say precisely what the following statement means, but the gist is the following. An abelian variety should be thought of, I'm sorry for that S, should be thought of as, and then a variety with a compatible group structure. Oh my goodness, this is terrible. Okay, so again, the example that you should have floating around in your mind is an elliptic curve, right? Okay, cool. So, right, so this is the gist of the theorem that we're trying to prove. And so our aim for the rest of today will be on precisely understanding what we mean by abelian variety. And by extension, we'll have to understand something about group schemes. So let's get into group schemes. Okay, so let me draw a line here. Okay, group schemes. Cool. So let's have S, a scheme. So I'll use throughout this SCH to denote the category of schemes. And the notation something is an element of category is sloppy shorthand for this thing is an object in that category. So let us be a scheme, then an S group scheme. is a group object, and I'll explain what that means. In schemes over S, which I will give the shorthand of just schemes sub S. So what does that mean? Well, it's an S scheme G, with morphisms. So these are S scheme morphisms. Multiplication. So this will go from 2 copies of G to G. Inversion. And an identity morphism, which goes from S to G, such that the following diagrams commute, right? So what we're going to do is basically abstract the axioms of a group, turn them into statements about diagrams commuting. So the first one that we'll think about is associativity, right? It's a little sloppy, it's okay. Right, so what's associativity about? Well, you have 3 things, you group them in different ways, you get the same answer, right? So here's one way of writing that. And again, there are lots of different ways that you could draw these diagrams. So, whatever is your favorite, go with that. Okay. So I could group the first 2 or the second 2. And of course, these are the same. Wow. Why does it do that? Okay. Right, so once we group a pair of things, we end up with just 2 things of the 3, right? So we could multiply the first 2 and then essentially do nothing. It's having a little bit of problem with latency. Sorry. Just a second. I think I'm drawing the things slightly too close together. I'll try to remedy that. Okay, so you multiply the first 2 things, then do nothing. Here, you do nothing. You multiply the first 2 things. That should be M. And you get the same answer. Sorry. Then you have to multiply. Right? So this is just saying you multiply a triple of things, grouping different ways, you get the same answer. Nothing surprising there. Okay. So then we have the notion of identity, right? And here, what we want to do is think about, right, what it means to have an identity, right? So you should be multiplying by the identity and getting the same thing. Okay, so you might start with G, but equivalently, you could start with G crossed over S with S, that's just G. And similarly, you could start on the other side, like this. Map your way in, right? So you do nothing on the first one, treat it just the same. And then how do you recover the identity element? Well, that should be given to us by our map E. Similarly here, we use our map E. This gives us 2 different ways to get to G cross G. All right. Here, we could just jump straight to our quote group element. So here we have a projection map. So I'll write PR1 to say project onto the first factor. And this will be a PR2. And then the claim is that this commutes. This is what the identity axiom looks like in group scheme language. Again, nothing too surprising. Honestly, none of this should be all that surprising. I just want to go through this for people who are not familiar. Again, there are notes that I have available where all this is going to be spelled out. So if you're not quite getting this, then just take another look at that. Okay, so then we have inverses, the final chapter here, right? And again, there are lots of ways that you could go about this, but the first thing is, how do we actually recover the identity element, right? We're saying there should be something that when you multiply by it, I give you a group element, then its inverse should satisfy that, you multiply and you get the identity. So one way to actually recover the identity is to just do this, right? Okay, so then we're going to say that some other process is going from G to G recovers the same thing. And one way that we can do that is to take two copies of G, use the diagonal, and then down here have G cross G once again, which we map via multiplication. And then there are two ways to get here, right? Because you can multiply by an inverse on the left and an inverse on the right. So there's an inverse on the left and an inverse on the right. And then this recovers for us the same answer. So again, hopefully this gives you just a rough feel for, the way in which we think about group schemes, right? Or one way that we work with group schemes. You translate what you think into functorial language like this. I will note though that there's another way that you can think about this, and it's also a very useful way. So I'm going to scroll past this. So basically, by Uneda's lemma, this is the same as a, quote, functorial group structure. On the functor of points. Which I'll write as H sub G. And the way you should think about this is that it's morphisms in the category, I guess, this case of S schemes from something to G, right? So functor point says, give me all the maps to my thing. So what does that mean? Well, i.e., it is a group structure on Hg of T, which again is often written as G of T, functorial in T. Which is an S scheme. Cool. And there's even one more way we can write that. So there's a factorization. So again, you have schemes, I guess in this case so for S, sets, right? The functor of points takes the opposite to sets. Then down here we have the category of groups, which I'll write as GRP, which has a forgetful map. We get a factorization like this. That's another way to think about what a group scheme is. So then similarly, when we have our group scheme, we can insist that it be commutative, right? Because just like not all groups are abelian, not all group schemes are commutative. So what do we mean by commutative? Well, it should mean that the order of multiplication doesn't matter. And again, you could go through the whole functorial nonsense and write down diagrams, write down a diagram that needs to commute for that to be the case. I'll just say that two simple things. So G, an S group scheme, is commutative if if Hg has a functorial, whoa, that got funky. Hold on, there it is. A functorial abelian group structure. So here the key part is it's abelian. which is equivalent to, again, a factorization like the above. So op set, or, well, yeah, it's fine. It's G, and then here we have the category of Abelian groups. Where again, this is forgetful. Okay, cool. So that's what a group scheme is. So let's give some examples, right? There are lots of examples. I'll give three, two of which I will use a lot. So the first one, so I guess I'll say one, is the additive group scheme. Blackboard bold GAS, which I'll just say GA because S should be clear from context. It has the following relation, or the following property. So GA of an S scheme T, sorry, that should be parentheses. There we go. This should be, just give me that, right? Which is a group under addition, okay? And this is represented by so I guess let me say this. We're gonna put this, I'll put it here. So for simplicity, S is spec R in these examples. So if we're saying S is spec R, then the thing that's representing this additive group scheme should be R adjoint T. Okay. So then two, for consistency, I'll put it over here. All right, we have the multiplicative group scheme, which is GMS or just GM. And it has the functorial property that GM of T in S scheme is the units of the ring of global sections. So this is a group under multiplication, and it's represented by, well, in this case, a punctured line, right? So spec of R adjoint T plus, ooh, it doesn't like that one. T plus minus 1. There we go. Okay. And then the final example that I'll be using a lot is the, I guess, the mth roots of unity group scheme. It's not elegant, I guess, but it works. Sorry, guys. Mu m s, and I guess this should be script m, is mu m. Where again, m here is, say, a natural number. So then mu m of t, well, give me f global sections that are units such that f to the m is 1. Okay. This is represented by what exactly? Well, no surprises really. Spec of R adjoint T mod T to the M minus 1. Okay. And I'll note that all these examples of group schemes are, in fact, commutative. So that's important. All right. So whenever you have a category, you need to know about your objects, but you also need to know about your morphisms. So in particular, we need to know how we map between group schemes. So that's hopefully not very surprising. So I'll say a morphism of S group schemes guess I'll underline the whole thing, is an S morphism, by which I mean an S scheme morphism. Man, S is tricky. S. Let's say phi from a group scheme G to a group scheme H, such that, well, again, there are a lot of ways you could say this, but I'll just say this. So you can multiply it on the level of G, and you can multiply on the level of H. Wow, that's so weird. There we go. Right, on the bottom you have phi, and on the top you get the induced map phi cross phi. And we want this diagram to commute. So I know I've used this notation already. This swirly arrow means that it commutes. Okay. And again, this is basically the same as saying that, if you take the perspective of having a functorial group structure, then you're just saying that you have a group homomorphism on all of those guys, and it's compatible with the change, changing from one T to, let's say, a T prime. Okay. So, something that is true across most of this theory is that a lot of your intuition from group theory carries over. And a lot of the proofs carry over because, again, you do the same proof and then you note that functoriality is preserved, right? So we have, I'll say, expected relations. Like what? Well, I mean, things like if you invert first and then do your morphism, then that should be the same thing as inverting second and doing your morphism, and that's true. I don't know why I bothered to fix that. Anyways, so you have things like this. You can go crazy deducing other relations from group theory. And there's some really good books, like one by Lenstra on theory of group schemes. Okay, so something important to talk about, right? You have your morphism. You need to know about its kernel. Turns out in this case that the kernel exists, right? So, again, because group schemes are these functorial objects, right? I mean, if I scroll up to the examples, I sort of told you what it should do if I plug in a group scheme. Sorry, if I plug in a general S scheme T, and then I said it's represented by something. And here, it's not important that this thing is affine, right? You could sort of do this construction affine locally and build the group scheme over any base. So, it's fruitful, as it often is in algebraic geometry, to think of group schemes in terms of what they do functorially and then proving that they are representable, right? So basically, if we think about the kernel, right, we can describe what we'd want the kernel to do as, say, a space, right? So something that takes in schemes and spits out, I don't know, sets, right, or groups. The kernel should be thought of as satisfying the following property. And that should be a curved line. There we go. Cool. If I give you an S scheme T, so this will be for all S schemes T, then I should just be recording the kernel of, well, the corresponding map on the level of T points. Cool. So this space, kernel of phi, is representable, and it's represented by the fiber product of the following diagram. So I have, on the one hand, G to H, no surprises, and then I have S, mapping down via EH, right? Take the fiber product of this, which, you know, as an S group scheme, and then it turns out that it has the right property, which is this. And you can verify that. Okay, cool. So this is sort of our functorial group theory, if you will. And the last thing I'll note, and this is maybe a bit more technical, or at least, you know, doesn't immediately flow from just thinking about group theory, but we'll need it anyway, is something built up by the following proposition. And I don't actually need to write down all the properties that are there. You can see the notes for that, so I'll just summarize this. So if I have a group scheme over a field, right, which again, abelian varieties are going to be examples of these things. So these guys have a lot more structure than your average group scheme. You know, for example, they're necessarily, well, no, I'll get into that later. Okay, so you have a K group scheme. Well, then there's a, let's say, I should just spell it out, a canonical closed K subgroup scheme, which I didn't formally talk about what subgroup schemes are, but I guess it's an exercise to write down the appropriate definition. There exists a canonical closed subgroup scheme. Okay, let's say G naught inside G, and I'll just say built from the connected component of the identity. You know, which if you're thinking about schemes as locally ringed spaces, then this is saying, wow, oh, I know it's wrong, I know it's wrong. I think I have solved my problem. Okay, right. So connected component of the identity in G, cool. All right, so what do I mean by the identity in G? Well, in this case, we have spec K is mapping to G, BR map E. Well, this thing is a point, its image is a point, that point is the identity. Oftentimes, we will identify that point with E itself. And you know, here what happens is that you basically take the underlying set or even underlying topological space of G naught to be the connected component of the identity, and there's a nice way to put a group scheme structure on it. Okay. So the reason why we care about this kind of thing is that, well, when we talk about Picard schemes and when we talk about dual Abelian varieties, it'll be important. But yeah, I'll leave it at that. If you have intuition from Lie groups that, you know, what happens on a neighborhood of the identity is sort of capturing most of what you need, modulo some conditions on G perhaps, then the same sort of thinking applies here. All right. So let's actually get to talking about abelian schemes and varieties. Although I guess before that, are there any questions from anybody?
I got maybe a quick question about the roots of unity example.
Okay.
So how come you don't add G inverse, or is that just part of that quotient? If you're looking at units in your set.
You don't add T inverse. Oh, shoot.
I'm wondering, I'm not sure. Yeah.
I believe you want T inverse.
Okay.
Do you really need T inverse? Isn't T to the M minus 1 just end up being T inverse?
Right. It feels like it just.
Oh. Yeah, of course. Yeah. You don't need it. You don't need it. You got it.
It's just redundant, but it's there. Okay.
Yeah. Sorry about that. Yeah, of course. Thank you, Des. And any other questions? Okay, cool. So let's get to talking about abelian schemes and varieties. Okay, so I guess I haven't been using definition up into this point because that was all sort of, in some ways, one long definition. I think I will get into using definition more now, though, because the lines will be a bit clearer. So I'll just say that an abelian scheme over S, where S is again a scheme, is, well, it's a smooth proper S scheme with geometrically connected fibers. Yeah. I'm sorry to that C. Okay. So we're by geometrically connected, I mean, if you base change to the algebraic closure, then the fiber becomes connected. Okay. So then if S is spec K, geez, S, come on. For K of field, we get the notion. I see there's some questions in the chat. Oh, okay. All right. If we take our base to be spec K, we get the notion of an abelian variety.
Do we want to add that this thing is a group scheme? Or
Oh,
a
sorry.
group scheme?
Yeah. Sorry, I should say group scheme. Well, I guess I have an eraser, so. There you go. Yes, thank you. Very, very important. Okay. So, you know, yeah, what's up?
When you said connected fibers on the algebraic closures, you meant take the closure of the residue field, right? Is that?
Yeah, so if you think about the fiber, then yeah, the residue field at that point, or I guess the residue field is recovering for you the fiber, and then you can base change the algebraic closure of that.
Good.
Okay, so we think of abelian schemes as families. S is just hard. Okay, families of abelian varieties. I guess B is hard too. Parameterized by S. Cool. Right.
Zach, sorry, what do you mean by geometrically connected fibers?
So what I mean by geometrically connected fibers, right? So you're familiar with the notion of fibers of a scheme? Or rather, this is a map of schemes, right? So really what's happening here is that I have, let's say, pi from A to S, a structure morphism, right? So it's an S scheme. This map's smooth proper. It has fibers, right? So one way you can think about that is I take a point of S, you know, so if I take some P in S, then there's an associated, let's say, kappa of P, which is the residue field at that point, right? Think of it as a locally reduced function.
Oh, okay.
Right?
Okay, so if like S is spec K, then it's just saying it's a geometrically connected scheme.
Yes.
Okay.
Yes.
Okay. Thank you.
Yeah, no problem. You know, and again, like equivalently to thinking of the points here, you just think of maps from like fields into your, you know, spec of a field into your thing. Okay, so I'll keep those there, not a problem. All right. So, well, yeah, this is fine. Let's start with our mark. All right. So you can see the notes for this. It's not difficult to prove. It's only a few lines, but so morphisms of abelian schemes, right, which are just morphisms of the underlying group schemes, are always proper. And you know, what do I want to say here? Let me think for a second. Yeah, this is fine. So let me say morphisms F of abelian schemes are always proper. So, you know, this implies, because properness is preserved by base change, that the structure morphism of the kernel is always proper. And I think I forgot to say this before, but the kernel will always be a locally closed subscheme. So it has a nice structure to it. This is always going to be proper. And if we want to check things about F, like its finiteness, then it suffices to just check if the fibers are finite, you know, and by doing translation and stuff like that, you can see the kernel's a finite group scheme. So, you know, so finiteness of F be the same as finite fibers, again, by properness established just a second ago. Man, S is quite a challenge. There we go. And this is if kernel F is a finite group scheme, again, by translation, right? So the fact that we have translation makes things a whole lot easier. And again, in the theory, you know, if you're thinking about Lie groups, you only really need to check things on the neighborhood of the identity, because you can just translate by the group action to get elsewhere, or by, you know, by your group multiplication. Group schemes have a lot of other structure, and sorry, abelian schemes have a lot of other structure that I won't get into. Again, it's laid out in the notes. You know, like I note like why things in the theory and stuff like that. It shouldn't be very surprising. They have a lot of nice structure to them. There is one important thing I want to say, though, which I guess is another remark, but I'll just include it here because we're already in a remark, which is that some sources require one of two things from abelian schemes, right? So they might require them to be geometrically integral. So let's say geometrically integral. But this is automatic, and I won't get into it, but it's not tricky at all. It's not tricky at all. Or projective. Right, they want it to be a projective algebraic group, and the only part there that really matters, or that's not trivial, is projectivity. We will verify the latter later. So we will verify the latter later. It's not immediately obvious that abelian schemes should be projective. All right. So.
Sorry, Zachary. I'm always a little bit confused about, I guess, projectivity. So in this case, what does it mean to be projective over a base?
Okay. Let me just avoid this question and say Abelian varieties.
Okay. Okay, thanks.
Yeah. I could give your question an answer, but it's not necessary. Okay. So what's an example? I've been floundering around, but let's get some examples. Okay, well, the classic one, we'll leave the colon like that. Elliptic curves. which I feel like deserves an exclamation mark. Right, I mean, there's maybe a bit of work depending on how you define elliptic curve, right? If it's a smooth projective genus 1 curve with a distinguished k-rational point, then you can use Riemann-Roch and resulting theory to show that it is a group scheme, and that k-rational point plays the role of the identity. Hopefully this is a picture that's familiar to most of you. And in particular, what we see is that elliptic curves are the one-dimensional examples of abelian varieties. And, in the notes I'll leave it as an exercise, but again, it's a pretty simple one. You can think about the notion of, what an elliptic curve, quote, should be over a general base, right? By which I mean, how do we think about a family of elliptic curves? And that's probably not very difficult to figure out, but I encourage you to do so. Let's get another example. Okay, yes, so we'll talk about Jacobians. So let C be a smooth, proper K-curve. Sorry, with genus G. So, it's Jacobian. All right, I'm going to pan up. This should be a scheme satisfying, well, that if you take its k-rational points, you should get the degree 0 line bundles on, whoa, not on K, on C. Yeah. And this should be functorial, right? So like if I have a field extension, maybe a finite degree of K, then this should be the degree 0 line bundles on C base changed, right? So then if K itself is the complex numbers, then I don't even know what happened there. Jack of C may be identified with I guess I'll call it the analytic Jacobian. So this will be omega 1 de Rham. Shoot, sorry. What am I even doing? Okay, right. So I take the de Rham 1 forms on C, dualize that, and then you're going to mod out by the singular cohomology of, the singular homology of C. And I guess this is induced by the embedding. Well, I mean, how do you embed the singular homology into your de Rham 1 forms? I guess they're dual. Well, you take your guy, which, what do I want to call it? Class of sigma, let's say. And you integrate against it, right? So maybe I'll write dot to indicate that you are going to plug in forms. Okay. So then, it's an exercise to verify this, and that, what do I want to say here? Right. So in the complex case, you can verify that this quotient is a complex manifold of dimension G, where G was the genus of our curve. And what we'll see in the future is that the Jacobian is actually just the dual. If you plug in not a curve C, but well, sorry. So that's being unnecessarily boring. If you plug in a scheme with suitable properties so that its Picard scheme exists, then the pick 0 is actually the Jacobian, which maybe isn't surprising because pick 0 appears here. Okay. Cool. Sorry if I lost anybody there. All right. I will note that it's actually a bit difficult in practice to give examples of abelian varieties that aren't Jacobians, or they aren't duals, essentially. They do exist, and if you're curious about it, I mentioned a paper in the notes that you can go check out. Yeah, there's some cool stuff there, but know that they do exist. Okay, so then another definition. So let's have A over S be an abelian scheme. You can tell that I'm shifting conventions as I go. Let's have T be an S scheme. And let's pick a T point of A. Cool. So then we get left translation. It's, well, a morphism from A base change to T to A base change to T, you know, given by the composition so we take AT, we identify it with, well, T crossed over itself with AT, no surprises. And then we need to move to 2 copies of our guy. These are crossed over T as well. And then finally we move here by multiplication. Okay, what is this nonsense? So all that we're saying is take your point, think of it as just, well, you know, this is just for bookkeeping purposes, really. Really all that you're saying is put a copy of X on the left, take your thing on the right, multiply them, i.e. add them if you're writing your addition or your group structure additively, and that's what the morphism is. If this sounds a little confusing, then this is literally given by translation if you look at the functor of points, right? So just like just about everything we'll talk about in relation to this stuff, if you look at the functor of points, it's all very clear what's happening. So, you know, if you're scared or whatever, look at the functor of points. It's doing what you think it should be doing. Okay. So that's translation. Why do we care? Well, because translation encodes the structure of morphisms of abelian varieties. So, you know, this is basically the last leg of what we have to talk about, so I'll try to spell this out very clearly. So it's a theorem, which I'll call rigidity, or the rigidity theorem, but know that there are a handful of results that go by the name of rigidity theorem, in the context of abelian varieties. This is one of them. All the rigidity theorems tell you something about restrictions on the structure of morphisms of abelian schemes or abelian varieties. So that's what the rigidity is that, you know, you can't just do arbitrary things. Okay, so we're in the context of abelian varieties. Let's have X, Y, and Z be K-schemes with X proper. And I'm going to write down the technical conditions, but I'm not going to offer a proof here for time reasons. I have a reference in the notes, but know that most of these, I think all these hypotheses are necessary in the sense that if you check the reference, there are examples of what happens if you don't have those hypotheses. Let's have X, Y be geometrically integral and finite type. So when I write ft, it'll mean finite type. Okay. So then we have a map f from x crossed with y to z, a k-morphism, right? Such that, well, for some algebraically closed extension, let's say k over k, so almost certainly an infinite degree extension, and some rational point, why not, in y of k, that's sloppy, that should be a capital K, satisfying what? Well, such that the restriction, so I'll write f, why not, to be, the restriction to f, or to x crossed with y naught, let's say, which is defined on base changes. It's constant. I'm sorry, I'm struggling to write this. Right, to something, it has some image, let's say. Then what we find is that f is independent of x. Sorry. So let me explain what I mean by this, right? So we have our guy here, x crossed with y, no problem. We have z, and I guess I don't want x here, I want y, right? So we can map down here by just projecting, no problem. We map over here by our guy f. Okay, what we want is a map G here so that this commutes, right? And in particular, what you find from this result is that this map is unique. But basically, saying it's independent of x is saying that you could have just defined everything on y. All the data of this map is captured there. So why does this matter? Well, what this says is that, if I have a constant, sorry, if I have a family of maps, right? So perhaps doing this backwards, I should have said this first. So this map F, right? What do we think of it as? Well, one way to think of it is a family of maps from X to Z, right? Parameterized by Y. And if we're saying that one map in the family is constant, then in fact, the entire family is constant, right? So here we're thinking of constant meaning like it has a constant function. Its value is constantly a function from X to Z, if that makes sense. So we're saying if it assumes that at one point, then it assumes it at all of them. I realize after saying that that's not the best way to describe it, but again, the notes have a more precise statement of what that is. Hopefully that makes sense. And I'll note that this rational point, sorry for constantly scrolling up and down. This rational point, why not, right? Here, will often be obtained by, some k rational point, little k, and you just pull back to k bar. So, really, I think in a lot of settings, we don't need this level of generality, but behind the scenes, we do need a bit more for Galois descent reasons, but I won't get into that. Okay. So why does this matter, right? here's why it matters, corollary. And this is, again, sometimes called the rigidity theorem itself. So let's have A and B be abelian S schemes. Okay. So then let's have F from A to B. This is just an abelian schemorphism. Okay. So then, and actually, it's kind of important that this is not the case. So it's not an abelian schemorphism, it is an S schemorphism. Then there exists an abelian schemorphism. Phi from A to B, such that, well, F is basically phi, but you know, what's the furthest it could be from being if F was to be a morphism of abelian schemes, then of course we'd have to preserve the identity. So we need to actually ensure that that happens, right? So there's a small modification that's needed. I'll say this is F of E sub A. Or again, I'm thinking of E sub A not as the map itself into A defining the identity, but the image of that map. Okay. So basically, after you shift, then your morphism is an abelian schemorphism. And in particular, if your thing maps the identity to the identity, then it is an abelian schemorphism. So that's very important. So how do we prove that? Okay. So again, by translating it first, we can assume without loss of generality that F of E sub A is just E sub B. Okay, so then we want to show that F itself is a morphism of schemes, of abelian schemes. So how do we do this? Well, let's consider H defined from A cross A to B by what? Well, I'm going to write something that's sloppy, but again, it makes perfect sense on the level of the functor of points. In fact, this is exactly how you would write it. It's this. You know, so if you really want to be precise here, right, you could use your inverse map I, and you could use multiplication and composition and write some long string that records the same information. But you know, this is the essence of what we care about, right? We're looking at this kind of map. And what do we know about it? Well, we know that H has value EB on on EA crossed with A and on A crossed with EA, right? I mean, this is clear. You know, you restrict to the identity one of the factors, and then boom, it's all nice. So we're going to use the rigidity theorem to deduce that this map H is constant, which says that F is a morphism, right? Because it will say that F of A1, A2 is, oh shoot. Have to account for this sort of thing, sorry. Technically, this should be like this. Okay. Right, because if you remember from basic abstract algebra, they have the, you're thinking about inverses, you think about in terms of socks and shoes, right? You take them off in the opposite order, you put them on. Okay, so the rigidity theorem provides us with two commutative diagrams, right? So on the one hand, we have A maps to A, it maps to B via H, and then down to A. How? Well, project under the first factor, and there's a unique map G1. At the same time, so let's say it's commutes, we have a diagram that looks like map down to the second factor. You get G2 just the same. Okay. Hopefully it's clear what happens just from this, right? Basically, our map H is independent of both factors. That has to mean that it's constant, and the value that it assumes is EB, so this thing is constant with value EB, right? So it's basically H is constant with value EB, and that implies that f of A1, A2 is f of A1, f of A2. Cool. And then our tombstone. Awesome. There are a number of corollaries of this. Some of them I won't write down because it doesn't really matter for our purposes, but I encourage you to check it out. The one that does matter, though, is this, right? So earlier we defined what an abelian scheme is, right? And well, from a historical perspective, the reason that abelian appears in the name is because it's named for Abel, because he studied not these things themselves, but a precursor, if you will, or theory that ended up leading to this field being developed. You know, we'd like these things to be commutative or abelian in the group sense, and that's true. So the corollary is that let A be an abelian scheme, then A is commutative. And I'll note that, you know, we'll use the rigidity theorem. The rigidity theorem we wrote down was for K schemes, but you can work fiber-wise, right? So in all these cases, here things were defined over K. Here we're working with abelian schemes. You can work fiber-wise here, and similarly, you can work fiber-wise down here, and you get that your thing's commutative. So really, this should say commutative. I should say abelian variety if I'm to be entirely rigorous without doing more. And the proof is extremely simple. So gosh, this is a pain. Sorry. So apply the above to inversion. Well, A in this case, from A to A, right? So what we know is that inversion maps the identity to identity, so it's automatically a homomorphism, or you know, an S group scheme morphism. And if you think about it, you know, again, from basic group theory, we know that there are groups abelian if and only if inversion is actually a group homomorphism. And the same thing is true here. Again, you just work functorially. But yeah, so that tells us that abelian schemes are commutative. And you know, I guess the final thing that I'll say about that is that, you know, there are a couple of things that you could, or different ways that you could go about proving this result. This is one. A different one would be to think about the action of conjugation and then to show that it's infinitesimally trivial. So again, I don't do that here, but actually some of the ideas that are used in that proof are quite nice and do have applications later on. Again, it also draws parallels to Lie group theory. So I invite you to check the notes and look at the reference for that to see more about that kind of proof. But yeah, so this is the basics of abelian schemes and varieties. Sorry for the technical glitches. I think I've figured out how my pad works now, so hopefully tomorrow and going forward I won't have the same issues. But yeah, I think that's where I'll stop it for today. So are there any questions from anybody?
Zach, you may have mentioned that earlier, but those separatedness and finite type hypotheses, are they always satisfied by group schemes, or is that by abelian schemes, or is that only for varieties?
Well, let me find my pan button. Okay, let me jump to where I'm talking about. Actually, screw it. Use my mouse. Okay. Here?
Yeah.
Well, so abelian schemes are smooth, right? So that automatically recovers the finite type hypothesis.
Okay.
And then them being geometrically integral is something that I mentioned before in a remark, I think. Yeah, to be geometrically integral or projective. So them being geometrically integral, so they're geometrically connected, right? And because they are smooth, they're reduced. And I believe it's a general result that if you're reduced and geometrically connected, then you're geometrically integral.
Okay.
Yeah.
And separatedness is?
Separatedness comes from the fact that you're proper, right?
Okay, cool.
And it's part of the definition.
Cool, thanks.
Yeah, no problem. Yeah, a general rule of thumb for this theory is that, you can generalize a lot of it, such as Rigidity Theorem, to settings where you have these certain hypotheses, and then it's maybe not surprising that abelian varieties do satisfy rigidity, because you're putting a lot of conditions on them, right? I mean, you're requiring them to be smooth and proper and geometrically connected and have a group scheme structure. So chances are, if you think it has a property, then it does.
Fair enough.
Any other questions?
Does it equal to its Jacobian?
So in the one-dimensional case, so for an elliptic curve, yes.
Right.
But if you're higher dimensional, then that need not be the case. Your Jacobian will be your dual.
Okay.
Your dual will always be isogynous. It will always be
But-
isogynous.
But you'll be, okay.
They need not be isomorphic.
But they're very close.
Yes, they're very close.
I mean, you can recover it from the Jacobian. This makes sense.
Yes, yeah, by you have auto duality, right? So
Yeah. Do they look very different from in prime characteristics?
Yeah, that's an interesting question. So it's maybe a bit surprising a priori that the dual is smooth in positive characteristic, because the general Picard scheme, if you will, need not be smooth in those cases. But it turns out that the dual will always be smooth, so it will be an abelian variety. So that's maybe the first inkling that the theory achieves a lot of the same results, but does have a different flavor in positive characteristic, if that makes sense.
Mm-hmm.
So you have to work a bit more generally. So I'll say this. There are a lot of tools that work in characteristic 0 only. And then there are tools that work in any characteristic. And I will take, characteristic, I'll take all characteristic methods for what I'm doing here. But smoothness will be something that proceeds in all characteristics.
I see.
Yeah, because if not, like if you're in characteristic 0, there's a result called, or there's a theorem of Cartier, which says that any finite type commutative K-group scheme is smooth. So, and the argument there is pretty straightforward. So,
Is that not true? Wait, any finite type reduced K-group scheme is smooth. Yeah, because you can just K adjoint epsilon by epsilon square.
Oh, sure. Yeah, I guess if you can guarantee that the reduced locus is not empty, then that should.
Yeah, exactly. Wait,
Yeah,
so does that not work in prime characteristics? I thought that's just a general theorem because the group look the same everywhere.
No, I think that fails.
Oh, is it because like it doesn't have to be like if it's reduced, it doesn't have to have a smooth locus, right? Because if you have a smooth locus, then it all looks the same.
Yeah.
So why is that? Or you can't? Okay.
I'm not. Let me get back to you.
Yeah. Okay. Yeah. No, that makes sense.
Any other questions? Okay, I guess I'll say this. So today again was mostly preliminaries, maybe a little bit boring. Going forward, we will be doing a lot more number theory, a lot more geometry. So, you know, if this is not quite your flavor of things, then hopefully that will shift, especially when we do weak Mordell-Weil stuff. I think that'll be pretty exciting. But yeah, that's all I got for today. So I'll stick around for a little while in case people do have questions or want to chat. But otherwise, you know, thanks for coming today, and hopefully I'll see you tomorrow.